All right. So on Friday and Thursday last week, we were talking about the binomial distribution. Okay. And if you remember, a binomial distribution had four things that we had to make sure existed within the scenario to be classified as binomial. We needed a fixed number of trials. We needed two outcomes for each trial. We were calling those successes and failures. The outcomes were independent of each other, and therefore it allowed the probability of a success to be constant for each trial. Okay, and those are the four things that needed to be maintained every single trial, and then we have a binomial distribution. Okay, so one of the things that we're interested in on Thursday and Friday of last week, all we did was work on determining what the standard deviation was, what the mean was, those two things. Okay. Now we actually want to find probabilities. Okay, so we can use binomial distribution to find probabilities, and we're going to use this formula here. It says in a binomial experiment, the probability of exactly X successes in N trials is this somewhat nasty looking formula. Okay. Do you guys? So let's just kind of pull this formula apart real quick. Do you guys know what factorial means? If I say n factorial, so let's say n is like 6. What that means is 6 times 5 times 4 times 3 times 2 times 1, right? So it's going to take that number. That's going to be your largest factor, and then you multiply by all of the natural numbers that are less than that. Okay. So this part right here, that part right there, is actually what we refer to as a combination. Okay. Let's see here. Kind of give you a scenario of what a combination does for us. Well, just a minute. There you go. Okay. So this here is a combination. Okay. And what's nice, that's a nasty looking formula for us. So there is a function on your calculator that encompasses this formula. Okay. Basically what we're going to do is we call it, let's do it this way. Let's go. We had a question earlier about like taking a quiz and guessing on every question of that quiz, and ask, okay, what's the probability of getting a 50% on that quiz? What's the probability of getting 6 out of 10? What's the probability of getting 7 out of 10? Those types of things. So what we do is n is your number of trials. So I'm going to say 10, and then we use a capital C, and then this is going to be the number of successes that we're interested in. Okay. So a lot of times, and our formula is going to be this in our calculator. It's n, and we say combination R. Okay, and that's a it's basically it's a counting technique. Okay, which allows us to go through and say, okay, how many different ways can I take a test that has 10 questions on it and get them all wrong? That's what this is saying. That's what 10 combination 0 means. How many different ways can you do that? Just one way, right? That's the only way that you can do that. So let's just see. Let's make sure that when we take our calculator. Okay, so I'll show you. And there's Desmos has, obviously you guys don't have your computers, but Desmos would allow this. I can't even get to Desmos. So I'm going to use the TI 8384. It is the same on these red calculators, if you have something similar to that. Pretty much all your TI 30 calculator, TI 30, TI 84, are going to have this. Okay, on your TI-84, what you need to do is you need to type in. It's kind of goofy, and some of you, if you've got the newer TI, like the colored TI, you might be able to change this a little bit. But I'm gonna show you a couple different ways of doing this per the operating system that you have on the TI-84. If I wanted to go 10 combination 0, I'm going to type in 10 first. And now I'm going to go to, so everybody needs to go to math. And when I hit the math key, it's going to take me and give me these 4 options across the top. I want to go over to PRB, which is probability. And you see the third one says NCR. That's the one we want. Okay, and then I'm going to push 0. Okay, so the way this is set up, the way this operating system works is that it's attaching this 10 to that N and this 0 to that R. Does that make sense? And when I hit enter, you're going to see that it gives me that one way of taking this quiz and getting all questions wrong. Does that kind of make sense? Okay. Now, if you have, so let's see here real quick. Some of you might have, and I don't know if I've got this operating system here. Just the no, I don't. Okay, so some of you might have a if you click the mode button and you scroll down far enough, mine doesn't have 2 pages under this mode button. Okay, but some of yours will have a second page, and at the top of that second page it should say classic print or math print. Okay, if you have math print highlighted, what it's going to do is give you something like let's see here. It should give you something like that, where you can actually go. There's, I know some people might be having a hard time seeing this, but there should be like a dotted little box here that you can actually take your cursor and go and highlight and type in 10 in there, and then you can go and highlight in this other box and type in 0 in there, and it will actually calculate it that way. Does that make sense? So that math print is a nice feature if you have that available to you. Okay. Another way that we often see a combination being written is they'll use it like this. They'll say like 10 and then choose 0 that way. So you might see them stacked in like a matrix almost. But that would mean the same thing as this here, if you ever see it written this way. Okay, so what does this mean to us? So let's think about this. How many different ways could I take and do 10 combination 1? Meaning, how many different ways could I take this quiz and get one question right? 10. 10 different ways. So the idea there, if we're trying to process this, would be, let's go, let me just, so let's say these are the questions on the test, right, or the quiz. I could say I got this first one right, and then I got all of those wrong, right? That would be one way. Then I could take and say I got the first one wrong, second one right, and then the rest of them wrong, right? That would be a second way. And then I could do that. I could take this yes, and basically now the yes is going to be the third question. Get the third one right. Every other one would be no, right? And I go to the fourth one. Okay. So if I did that and I move that yes through there, there would be a total of 10 different ways to answer and get just one correct answer on this test. So if we do that with our NCR, oh, wrong button. So 10, math, probability, 3, choose 1. So there's 10 different ways. Okay. Now, what is it if I wanted to go 2?
45.
It's 45. Okay. And basically what this is doing is now saying, okay, well, I'm going to answer the first one yes, and then the second one yes. Okay. And then maybe this one stays yes. That one is now no. Got that one wrong. And then this one is yes. So maybe I keep the first question yes every time, and then allow that second right answer to kind of filter its way through. Does that make sense? And then the next one would be, well, let's say that we've got question 2 yet was correct. First one was no. Question 2 is always yes. And then let the second yes, or the second correct answer, work its way through. And we were to count those, okay? Count the many times that we can do that, the different groupings, we would have 45. Okay. Now, if we neglect the NCR formula, okay, or the function the calculator allows here, we would actually have to take our x factorial. Let's go back to our formula. Sorry, n factorial over n minus x factorial divided by x factorial. So n is the number of trials. So we're going to go 10. And then it would be times 9, times 8, times 7, times 6. Now, I don't want to type that in. There is actually another probability column again. There is a factorial. Okay, so I have 10 factorial, which would be, like I said, 10 times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. And we're going to divide that then by n minus x. Well, if I want to do 2, n minus x would be n is 10, x is 2. Okay, so this would be 8 factorial, right? Okay, and what's that going to do? Well, that's going to, if right now I got 10 factorial up top, and I've got 8 factorial on the bottom, everything from 8 to 7 to 6 times 5 is going to be up top, and it's going to be on the bottom, right? Aren't they going to cancel out? So right now, all I've got, because of this cancellation, all I've got is 10 times 9 up top. What's 10 times 9? 90. And then this says I need one more factor of x factorial. Well, x is 2 for us. Right, so you've got 2 factorial on the bottom, which is just 2 times 1. So you got 90 divided by 2 in this case. What's 90 divided by 2? It's the 45. Okay. This formula right here, this function in our calculator, has this formula built into the background. Okay. So you may see from time to time, this is, like if you were to Google like binomial distribution probability, you're going to maybe see this. You might also see something written like this. You might see N, C, and then they'll use X or R. A lot of times they use R. But then they'll say times P of X times Q of N minus X. Okay? Or you might see something like this where it says N choose X that way. And then they'll have P of X times Q of N minus X. Okay? This is just an alternative notation for saying the exact same thing that does. Okay? So those are a few different tools that you might recognize. Okay? Now, eventually, we will also use Excel. Okay? In Excel, all we have to do is type in the binomial distribution command, and then type in what our n is, what our x is, what our probability for our success is, and we're good to go, and it'll calculate all this stuff for us. Okay? But what I want to do is I want talk about a specific example that we've seen in the past. We have alternative ways of doing this problem, and I want us to see that the binomial distribution actually gets the same result, and because of technology, allows us to get the result a lot quicker than our previous techniques. Okay? So it says a coin is tossed 3 times. Find the probability of getting exactly 2 heads. Here it says make a tree diagram of how many outcomes have exactly 2 heads. So we've done this before. We've taken a coin and we've said, okay, on the first toss, we could have heads or we could have tails, correct? Okay. Then on the second toss, we could have heads or tails after a heads was realized first, or we could have heads and tails after a tails was realized first. And then on the third toss, it's the same concept. You could have had heads, and then on the third toss, heads or tails. Heads or tails there. Does everybody remember doing this? Yeah. Okay. So now just following this tree, we could have had heads, heads, heads. We could have had heads, heads, tails. Heads, tails, heads. And heads, tails, tails. Okay. The next one we could have tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay, so we have those 8 outcomes, right? Okay. Now, how many of those have exactly 2 heads? Be those 3, right? So the probability of doing this experiment and getting exactly 3 heads is 3 out of 8. 3 out of 8, or if we divide that out, 3 out of 8 gives me 0.375 as a decimal. 3 divided by 8, 0.375. Okay? Now, what is also interesting about this situation is that this experiment is actually a binomial experiment. There are 2 outcomes. Heads or tails, right? Those outcomes, the success is what we're looking for here, and we want heads. Okay? So that is a success, and it's 0.5, and it's always 0.5, right? Okay, so trials are independent. We've got 2 outcomes. We've got a fixed number of trials. We're going to do this 3 times. Okay? Therefore, we meet the criteria for having a binomial experiment. So if it's a binomial experiment, it should fit a binomial distribution. So we should be able to plug into our formula, okay, however you want to write this and however you feel like you're going to be successful with this formula. If you want to go n factorial over n minus x factorial times then p to the x times q to the n minus x, okay, that is our formula. And now n is the number of trials that you're going to go through. So we'd have 3 factorial over now 3. Now x, remember x is the random variable that values that you can take on. So we're interested in 2 heads in this case. Okay? So x is the 2. So we'll have 3 minus 2. Okay? And actually, I've got this factorial in the wrong spot there. Should be on the outside of the parenthesis. So 3 minus 2 factorial, and then times 2 factorial. Then times p. So p is the probability of a success. So a success is 0.5. X then is that we want that 0.5 to show up 2 times. So that's our successes. And then our failures is, in this case, still 0.5. But a failure is going to only happen 1 time. So that becomes that exponent. Is that going to make sense? Be 3 minus 2 in that situation. They're saying n minus x, n being 3, x being 2. So we can type that in. Now, this part, like I said, if you're going to use any of your calculators by hand, that part is nasty. So what I suggest is using the actual combination formula or function in your calculator that says 3 combination 2. This is always going to have to be your bigger number, okay, when you type it in. Otherwise, you're going to get, I think it probably gives you an error back, or it might say 0. Like if I have two, basically we're saying if I have 2 objects and I'm going to pick 3 of them at a time, is that impossible? Is that going to happen 0 times? Does that make sense? Okay. And then your 0.5 squared and then 0.5 to the first. That's a little bit easier to type in on your calculator. So if we do that, okay, we already know the answer to this question through our sample space. But if we understand that it is a binomial distribution, we should be able to say 3, go to math, over to probability, down to option 3. So 3 combination 2. Okay, and then I'm going to multiply that result. And actually, I don't know how it's going to work with order of operations here, so I'm going to put that in parentheses. And now multiply that by p to the second power, and multiply that by q to the first power. And if I've done things correctly, does it give me the same 0.375? Okay. So the idea here is when we do a binomial distribution, if we can make the connection that it is binomial distribution, it has those 4 criteria, we don't need to make the sample space. Does that make sense? Okay. And what would be, think about this, doing this trial, this flipping a coin 3 times, creating that sample space is not a difficult task. Okay. However, would it be hard to do the sample space of that quiz that had 10 questions on it? That'd be very difficult, right? Almost impossible. Okay. If I wanted to go back up to, which we will here in a moment, go back up to this question and determine what is the probability of getting maybe a 50 or above, 50% or above. A binomial distribution is going to allow us to do that much easier using this formula than it is to think about what the sample space looks like. Okay. Does anybody have questions on that, like the concept there? Always, I think it's just a good idea. Use that NCR function on your calculator. Like I said, if you go to Desmos, if you go home, it should be in, like you click the little calculator or keyboard in the bottom corner, and it'll bring up options. It'll bring up a bigger keyboard. Like I think at the top it says like miscellaneous. I think there's one that says stats. If you click that stats one, it should have an NCR option there if you're going to use Desmos. GeoGebra, if anybody is interested in that, I think it has NCR. So, and then I just got to say what is my n number. So I put in parentheses my number n, which is my trials, and then how many I'm choosing. And you see that gives me 3. Okay, so there's 3 different ways to take 3 or do the situation of 3 flips and get 2 heads. Okay. So just give you some different options there with your calculators. If we are in Excel, what is real nice about Excel? Let's zoom in so you guys can see this a little bit better. If I hit equals, there's a command, it's called binom, D-I-S-T, binom distribution. Okay, and when you do that, it says, what is your number S? Okay, so number S, what that is, that's the X in the formula. Okay, what are we? How many are we interested in? Okay, so we're interested in 2 heads in the situation. Okay, and then the next number says trials. Well, we're doing 3 trials. Then the next number says, what is the probability of S? What's the probability of a success? So that's going to be 0.5. Okay. Now what's nice about that is that we know it's binomial, so the way it's programmed is that it does use the probability of failure as well, but it's programmed to know that when I put 0.5 as a success, it automatically knows 0.5 is a failure. If I put 0.4 as a success, it automatically knows 0.6. It's using the complement in the background. Does that make sense? Now the next thing we want to talk about is it highlights the word cumulative. That's the next component or condition of this command. We want to actually type in false right now. Okay? Because cumulative, and I'll give you a demonstration what cumulative means here in a minute, but basically cumulative would be adding up everything up to 2. So it would say what would be the probability of 0 plus the probability of 1 plus the probability of 2. Does that make sense? That's what the cumulative would do. So now I hit enter, and does it give me the same 0.375? No. Okay. Now, here's what's really nice about this. Okay? If we can, because we're going to be interested in not just 2 heads or 2 tails. Maybe we want to know all the different situations. So we could have 0 heads, right? In this situation, we could have 1 head, we could have 2, or we could have 3. Those are the values that your random variable x could take on, correct? Well, if I go equals binomial distribution, okay, and now the number s, so that's the number of successes that we're interested in, is going to be that one right there. Then I'll hit comma, and the number of trials, we're going to do 3 trials, comma, probability of success is 0.5, and then we're going to go false again. So it's the same exact command I just typed in, but instead of actually putting and prefacing this to be exactly 2, we're going to let it be the value in these cells. So now there's a 0.125% chance. Okay, so there's 1 out of 8 that is just tails is what that's saying. Okay, if I drag this, then it shows the probabilities of each of my random variables. Does that kind of make sense, everybody? Okay, so let me show you real quick what that means to us in regards to like the cumulative. So if I'm doing a cumulative for, let's say, down here at 2, what it's going to do is take 0.375, 0.375, and 0.125 and add them together. So if I said equals binomial distribution, number of trials, or sorry, number of successes, 2, number of trials, 3, probability of success, 0.5, and then if I say true for cumulative, hit enter, 0.875 is the sum of those 3 there. Does that make sense? So it's that is the idea that it's the probability of 0 or the probability of 1 or the probability of 2. Does that make sense? Using our probability formulas from last chapter when we see the word or, it's addition. Okay? So that might be of benefit at some point. Okay, so let's go back to the question that dealt with the quiz that we were taking, and we were guessing on that multiple choice quiz. So if we're guessing on the multiple choice quiz, there were 4 options, right, for each question. Okay, so I'm going to hit equals binomial distribution. Okay, number of successes. So again, number of success would be 0 here, or A1. And then it says trials. We're going to do 10 trials. There's 10 questions. And now the probability of a success on this question was 0.25 because it was multiple choice out of 4 options. And then I'm going to go false. Okay, so as a percentage, what this is saying is that there's a 5.6% chance that I randomly guess and I get 0 out of 10 right. Okay. Now, as I drag that down, okay, this is telling me then that there is, like, if I guess there's a 14% chance that I'm going to get 4 of them right. Okay. If we go back to what we found to be the mean in this situation, our mean was n times p, right? Okay, so 10 times 0.25. So 2.5 was the mean, right? So if I go between here, would you agree that those, so that's kind of the region that 2.5 would be in, right? Is most of our data, based on the percentages there, are those the highest percentages that we recognize in that list? And that should match up to what we understand about distributions. Think about this. If I were to, and this is going to be a tool that I think is beneficial for us, I'm going to highlight these. And we'll go up to Insert, Recommended Charts. And this first one here gives us this histogram. Okay, it's a frequency histogram because this is showing us our it's a probability histogram that's showing our probabilities here, or we can think about it as frequency as well. But there's the probability of 0, probability of 1. So does your mean occur at 2.5 where most of your data is occurring, right? And our argument is, based on our standard deviation, let's see here. I think we still have it written up here. So our standard deviation was 1.37. So adding 2 standard deviations and subtracting 2 standard deviations gave us this right here, 5.23 and negative 0.23. Okay, so I'm going to round out to like 5.2. Where'd it go? There we go. So our mean why can't I color on this? Does anybody see why everything's grayed out? Anybody? Like, I don't know.
Probably not.
I think we should X now.
Well, it's been a great lesson, honestly. It really has.
Sounds like a problem.
Well, so 2.5 would be here. Okay. If I add my standard deviation 2 times, it's going to take me out to about right here. Okay. And if I subtract it, it's going to take me to a negative 0.2. Okay? So would you guys agree? So if we kind of visualize that, my mean here, and then 2 standard deviations to the left and to the right of it is going to basically encapsulate everything that is left to my cursor, right? Does that make sense? Would you guys agree that that is at least 75% of my data? Okay? And that's what Chebyshev's theorem says. It says from your mean, 2 standard deviations to the right, 2 standard deviations to the left, you should realize at least 75% of your data. And that's what we're getting here. Okay. Now, I'm using Chebyshev's because this is not symmetric. Okay. This is skewed to the right. Does that make sense? Okay. Think about this and think about, do these probabilities make sense? Okay, so this probability here would be a decimal, and then what we're going to look at 4 zeros and then a 9 as a percentage. So 0.00009%. Pretty low probability that you're going to get 100 on this test by just guessing, right? Okay. Not an impossibility, but it's most likely not going to happen. But that's what this formula for a binomial distribution allows us to realize. Is that right? So if you remember back to, and I said this I think on Thursday or Friday, if you remember back to geometry when I said there are questions that you might be able to articulate early on in statistics or probability analysis that might seem like a legitimate question that could be answered. But not until you learn maybe what type of distribution that question actually aligns itself with that you can actually analyze and find the probability. Like asking the question, well, what's the probability that I take a test and I guess on the whole thing get 100%. That's not a hard question to ask, but it's maybe a hard question to analyze without having this binomial distribution information. Okay, you could do it, but you need a sample space, and coming up with that sample space would be nearly impossible if I'm going to try to do that. Does that make sense?
Yeah.
All right. We'll stop there. Tomorrow, I want to go through and knock out these examples, and then that should get us to the point where we can start talking about the normal distribution, which is what the rest of the course is going to carry on with. Okay.